Anyway, I'm Doug Richards, and I'm with Atlantic University in Virginia Beach, which is a transpersonal psychology program. But this actually has more to do with my other work, which is in radio communication and how that might have an implication for anomalies research. So it's called Weak Signal Propagation Reporter, which is pronounced WSPR, Implications for Anomalies Research. And what you're seeing there on the screen is an example of where my signal can be heard with a tiny signal all over the world. So what is Weak Signal Propagation Reporter, WSPR? It's a signal processing algorithm for extremely weak radio signals. And there are hundreds of stations worldwide uploading to the WSPRnet database. So what you're seeing there is I am located, move my little arrow, maybe you can see that, over here on the East Coast in Virginia Beach, and with a very tiny signal, about as powerful as a little flashlight, I can be heard in Australia, Alaska, Hawaii, South Africa, Europe, all over the world. And what I'm going to talk about is how this would apply to anomalies research. So why is it relevant to anomalies research? Well, much anomalies research also tries to detect very weak signals. All psi research seems to have very weak phenomena. The Global Consciousness Project, again, very weak effects on random number generators. And then there are some interesting geomagnetic field effects, both on things like psi and on other kinds of human behaviors. Then we can use WSPR, either it can apply it directly to studies of the effects of the geomagnetic field and ionospheric resonances on biological systems. So again, that would be things like psi, but also we heard earlier in some talks today, heart rate variability is a very interesting thing to look at in terms of consciousness. And so WSPR can be used to measure what's going on in the geomagnetic field and these resonances, and that could be then used to correlate with things like psi performance and heart rate variability. And it can also provide a very useful methodological comparison to other studies of weak signals. So for example, what's the best way to analyze synchronization of global consciousness detected by random number generators? And so some of the things that have been done to detect these very weak signals with WSPR have potential applications for all of this other work that looks at very weak signals. Quick slide on how radio signals propagate in case you don't know. I have a transmitter there and a receiver and the Earth. And basically radio signals go around the Earth by bouncing off the ionosphere, an upper layer a couple hundred miles up in the atmosphere. And solar radiation affects the ionosphere. That's what produces geomagnetic storms, and it changes radio propagation. Now, it also seems to have an effect on psi functioning. So there have been studies looking at geomagnetic storms and their relation to psi functioning, and also various other aspects of human physiology. So the whole question of geomagnetic effects on humans is a very hot area of research, both in anomalies and in conventional research. And so being able to measure what radio signals are doing can sometimes serve as a proxy for figuring out what's going on with the geomagnetic field. Now, how does WSPR work? Well, the challenge, again, is that you have very low and uncontrollable signal to noise ratios in long distance radio communication. In contrast to, say, lab experiments where you can very precisely control SNRs, or they can be controlled or very high. But this is very similar to issues in psi experiments where you have, again, very poor signal to noise ratios. And so you need a way to deal with that. The solution as far as radio goes was this thing called WSPR, developed by a physicist named Joe Taylor at Princeton University. And it uses a form of coding called forward error correction and some other signal processing techniques to make possible decoding of signals 31 decibels below the noise level, which is way, way below the noise level. My signal and all the other signals used in this system, if you listen to it on the air, all you hear is random noise. It uses the ham radio bands with ham radio stations around the world transmitting and receiving signals, and then uploading spots of received signals to WSPRnet on the internet. And then the WSPRnet data can be downloaded and analyzed by anyone. So the intended application of WSPR is to explore effects of phenomena on radio propagation. This would be things like geomagnetic field variability, time of day, sunspots, time of year, sidereal time. And these same variables not only affect radio propagation, but they also affect human behavior and rhythms, including psi and health. And one of the nice things about WSPR is it's making measurements constantly. You can actually make measurements every 2 minutes. And so it's much more able to make fine-grained measurements than what's been used in the past, which are things called the K index and the A index. I won't get into any detail on what those are, but they are ways of measuring geomagnetic variability, but they only are updated every 3 hours, and they're only done from a certain very small number of stations around the Earth, whereas WSPR is capable, again, of looking at things every 2 minutes if you want to use it that way, and more typically every 10 minutes, and there are hundreds of stations all over the world, so you get a very fine-grained look at what's going on. So how do I do WSPR? Well, I'm a ham radio operator. My call sign is KN4NBI. Maybe some other folks are ham radio operators. And what I do is, using my radio, I send out a signal once every 10 minutes that's received all over the world. And everyone who hears me automatically uploads a report to an internet site called WSPRnet. Again, this is hundreds of people all over the world, and this is all automated. And then anyone can download and analyze the data for me or any other station. So I usually download data several times a day to have a look at it, but any of you could simply log on to WSPRnet and just type in my call sign, and you could download exactly the same data at any time. Now, here's an example of some of the kinds of data that I get. This is a download where we're looking at 4 weeks worth of data where a station called NV4NV is being listened to by me, KN4NBI, and it's a plot on the x-axis of days, 4 weeks worth of data, and signal to noise ratio on the y-axis. And most of what you're seeing there is just noise. This station is actually located quite close to me, and so the propagation of the station is generally not very good. We have very weak signals, and there's a lot of noise in there. So that's most of those green dots. But every now and then there's an incredible increase in the propagation. It becomes exceptionally good for about an hour or so. One time it was about 4 hours. And I'm not sure exactly why this is, but the interesting thing is this is much finer grain than looking at some things that can only be measured once every 3 hours. And so, for example, these might be very good times at looking for psi or doing a psi experiment in some of these times when you have this exceptionally good propagation. This is a question where the signal to noise ratio went up about 25 decibels, which is over 100 times better. So it's a major increase. So when we talk about things like psi being very unreliable, well, not necessarily any less reliable than radio propagation. Here you have a situation where in a time period of 4 weeks, there were 5 times when there was this exceptional propagation. So imagine that this was a psi experiment and it only worked when the numbers got above the 0 line there. You would have very, very rare occasions where it worked. And so again, this is a possible correlate. We don't know yet, but it's an example of how you can download this data and plot it and look for times that you might want to be exploring in more detail. Now, to change topics a little bit here, you can also use WSPR measurements as an analogy to psi experiment results, because again, we're looking at very, very low signal to noise ratios. And one of the things that has always bugged me is the people that say, does psi defy the laws of physics and is therefore not real? And so you'll see skeptics that say psi couldn't be real because of the inverse square law, because psi does not seem to depend on distance. For example, Reber and Alcock, who published a couple papers on that. And that's a complete misunderstanding of the physics, because that law, that inverse square law, applies to forces, like the idea that the force of gravity declines with the inverse square of the distance. For communication, that's completely irrelevant. The only thing relevant is signal to noise ratio, not force or field strength. And WSPR demonstrates this. I'll show you on the next slide, but my 100 milliwatt signal, which is less than your home Wi-Fi, can be heard in Antarctica because WSPR can decode at 31 decibels, minus 31 decibels of signal to noise ratio, way, way buried down in the noise. And so the next slide, I'll show you an example of what you get. So what you're seeing here is an example of how radio signal to noise ratio does not necessarily decrease with distance, which again is very similar to the results we see with psi. So this is my signal from Virginia Beach, received at various distances. And so signal to noise ratio is on the y-axis on the left, and the distance in kilometers is going across the x-axis. And what you see there is that at about 1,000 kilometers or so, there's a signal that pops up. And there are signals of equal strength at 2,000 kilometers, that's Texas. There are signals out in Colorado and in Utah and in California. And then even out in the Canary Islands, and even way out in Hawaii, 8,000 kilometers away, there's a signal that's only 10 decibels down. And so, again, no obvious dependence on distance at all here. Again, very typical of psi results, and it doesn't require there to be any strange quantum non-local effects. This is what you see in radio too. So the people that criticize parapsychology because the results do not seem to be affected by distance, that's very typical in radio. Also notice the wide scatter of points, that what's happening here is that you've got stations varying widely in how well they're received. Now, we still have issues with applying WSPR directly to psi experiments. In psi research, you don't have a way to quantitatively specify the signal level or the noise level, but from my previous slide, you can see that the inverse square law is completely irrelevant, that what we need to talk about is signal-to-noise ratio. In some models of psi is not, quote, a signal, but you can still apply the concept of signal-to-noise ratio. And you can't really apply the WSPR algorithm directly because it depends on time synchronization, which is not possible in psi experiments. But WSPR and its relatives are open source software and could potentially be modified specifically as an error correcting code for psi experiments. And WSPR can be used to measure physical variables relevant to psi experiments and other studies of other anomalies. So I'll show you a little bit about that now. So as I mentioned, WSPR may be more sensitive than standard indices like the A and K and AA indexes for measuring geomagnetic disturbances. And so I'll jump to the next slide here, which is just an expansion of the little picture there on the bottom. Here, a geomagnetic storm was predicted by the NASA folks who were looking at solar activity. But when it actually came to the date that it was predicted for a couple days earlier, in the what's called the AP index, no storm appeared at all. It was a fizzle. However, in the reception of my radio signal, the storm arrived exactly when it was supposed to and showed a very strong effect, again, showing that WSPR may be a far better fine-grained measurement of what's going on in geomagnetic variables than the standard indices that you pick up from, again, the 3-hour measurements. This is just a slide on Schumann resonances. I'm running a little bit out of time, so if you don't know what a Schumann resonance is, it's just another measurement of electromagnetic effects, and in particular, people are interested in it because the first frequency is right about near the alpha brainwave frequency. So it's been of great interest to some people looking at the effect of geomagnetic fields on human consciousness. And one of the groups that's done a lot of this is the HeartMath Institute group. They presented at SSE meetings in the past, and I found some strong relationships of geomagnetic measures in human physiology. And WSPR could offer an additional measure with finer temporal and spatial resolution. And that's just a picture on the right of a large number of measures that they were using, and certainly could add WSPR to those kinds of measures. Krippner and Persinger, quite a while back, were looking at some of the old dream telepathy studies that were done at Maimonides and found that decreased geomagnetic activity was correlated with high scoring in psi experiments. Again, WSPR might offer an additional measure with finer temporal and spatial resolution to look at these correlates with psi. And finally, this could be used to study other anomalies, anything where geomagnetic or astronomical variables might be relevant. So we've had no talks at this meeting yet on astrology, but WSPR might be helpful in measuring subtle solar and lunar and planetary effects on biological systems by looking at the effects on geomagnetic fields. And then another interesting one is UFO experiences. One of the types of measures that people have been taking is that of local geomagnetic disturbances. And WSPR is pretty good for looking at those in terms of their effects on radio propagation. And that's it.
Could WSPR be used to explore anomalous healing?
Again, it can be used for anything where you want to look at propagation geomagnetic type effects. In terms of what it's used for directly, it measures radio propagation. Although, as I said, for some kinds of experiments, like psi experiments, the source code is all open source. And I know people have modified it for a lot of other applications where you're looking at very, very noisy situations and signals. But as far as healing, if you wanted to know what is going on right now in the geomagnetic field and propagation around wherever the healing's going on, it could be a useful kind of thing to use to measure.
Okay. Another question. What are your thoughts about the relationship between whisper, psi, and stochastic resonance? Might there be types of geomagnetic noise that might boost the propagation of a posited psi signal? This was from
Well,
Eli.
what I found interesting just in terms of radio signals is the classic thing that ham radio operators are told is that when you've got geomagnetic storms, it inhibits radio propagation. And that was also the result they came up with some of the psi experiments. But what I found is that that's not entirely true. And sometimes geomagnetic storms greatly enhance radio propagation. And this is all on very, very short-term basis. So you may have a situation where for 15 minutes, you just have extraordinary propagation, and then it goes away. So again, the idea of whisper is you can look at it in very fine-grained measurements. Most people do it every 10 minutes to just not clog the radio waves, but the system can actually do it every 2 minutes. So you can be looking at small changes when you're looking at other kinds of resonances, psi, heart rate variability, anything you might want to look at.
Okay. Eli thinks that's an excellent response. Good job.
Great. I'm happy.
So here's a question from Stephen Hall, who really appreciated your discussion. He says, all about EM radiation local, but psi is often thought of as non-local propagation. And in a sense, this is actually a question I had. What's your position on the actual ontology of the psi signal as opposed to, the normal subject matter for whisper?
Well, I really have no idea in terms of the psi signal. And one of the problems is that I think that people make assumptions. And one of the assumptions is that psi is not distance dependent. And the idea was that, as I mentioned before, that that physical signals are distance dependent by the inverse square law. And I think I've shown here, that's not really true. It is for forces, but for information and signals, that relationship is not at all clear. It depends on lots and lots of things for ordinary EM signals, and we have no idea what psi is. And so suddenly saying it's got to be non-local because you don't get some nice inverse square relationship probably isn't true. Now, how far it goes, I don't know. Unfortunately, very few really, really long distance psi experiments have been done. Even Mitchell's experiment going to the moon, one of the things that this set of software, not just Whisper, but some other programs are used for, is moon bounce communication, where a ham radio operator in, say, Virginia Beach will bounce a signal off the moon and it'll go to California. And the same basic software is used to do moon bounce. And so coming up with a distance long enough to show that it has to be non-local is an experiment that's never been done. I'd be very interested to see what they get if they ever can manage to do it. Maybe Mars.
Yeah. So actually, there have been a number of remote viewing experiments, if you will, long distance, but the feedback on that's really hard. The verification is really hard. So who knows? But here's
also with the feedback for the remote viewing experiments. If, let's say, you do a remote viewing experiment to Mars and you see in remote viewing the same sorts of things that the Mars rovers are picking up, well, the way you know that is because they sent back a radio signal. And the way we can read the radio signals is by processing very much like this done on the radio signals. So you do run into an interesting feedback problem that any feedback we can get inevitably is by radio signals, even for really long remote viewing.
Yeah, that's true. Although, we won't get into that discussion because there's other questions.
Yeah.
So you may have actually answered this. Let me think. Oh, here we go. So Deb wants to know, have you run a psi experiment with Whisper and compared the data? I think you essentially said you hadn't, but if you want to elaborate on that.
I haven't run any psi experiments. One of the reasons is that when COVID struck, what I did is I started an ongoing 24-hour-a-day Whisper experiment that didn't require me to leave my house. And so I figured this is a great opportunity to work with something where I don't have to leave my house. It would be very interesting to use this, but I've not used it for that application. Instead, I've been collecting a lot of Whisper data and learning a lot about radio propagation for the last year and a half or so, which is why I'm offering this out to the community as here's something cool to look at. And maybe some people will think of some good experiments.
Okay, cool. So Eli has another question. He was wondering if you'd mentioned the lunar psi experiment. You did mention, of course. You've really thought this through. Very intriguing. I guess what he probably is looking for is maybe a brief description of what Edgar Mitchell did with that.
I don't remember all the details of what he did, but basically he had an experiment when he was a good way away from the Earth, far further than anyone could obviously get on Earth. He did a psi experiment, and as I recall from reading it, it was quite a while ago, it was a successful psi experiment. Now, one of the difficulties in all of this is the feedback issue, because what's been brought up, I even think in one talk at this meeting, is what you may be doing is using precognition on your own future experiences. And so if you got any feedback at all, then it's an interesting question. Was it long distance or was it seeing the future? And so I'm not sure. I'd have to look back at that experiment to see in terms of, do we really know what's going on? This often seems to be the case in a lot of psi experiments, is we're not quite sure what's going on in terms of, is this remote viewing in space or in time? Don't know.
Yeah, or both. There's an ongoing debate about that, and I
Right.
have one position that it's both. Other people are very determined to believe that it's just precognition. I think there's reasons not to believe that, but nonetheless, I have to apologize for Eli. That was not meant as a question; it was meant just as a comment. But that's okay. We got some more information out of it. Michael wants. Let me see. Yep, this is a question. So he mentions Shoshone shaman talking about electronic pollution and having to find places that block it to do some of his activity. Does this have anything to do with what you're finding? He wants to know.
Well, there's electronic pollution all over the place. In fact, I'd advise people move to Green Bank, West Virginia. That's the National Radio Quiet Zone, where you're not allowed to have anything because of the big radio telescopes. But the interference problem here at my house is just humongous. And it's things that ham radio operators are just very upset about. There's a plasma TV in my neighborhood, and whenever this guy is watching primetime shows, it just blots out everything. But power supplies, all those little wall warts, Wi-Fi, it's just become horrendous for ham radio operators in terms of the increasing noise level out there. Now, what effect that has on human health, I don't know, but it sure interferes with radio.
So just a comment from the early remote viewing research that kind of goes to this question. When the viewers did work when they were inside a Faraday cage, or very famously in Stephen Schwartz's Deep Quest experiment, they reported that remote viewing was easier in these shielded environments. So that may, again, we're talking a small sample size, but that may be an indicator of the effect that electromagnetic pollution has on psi experiences and such. But it'd be an interesting experiment to run a bunch of sessions inside a Faraday cage and outside of it and see what happened.
And again, it certainly messes up radio. I know a lot of people worry about this, and I don't know what. One of the things in my house, the variable speed motor on my air conditioner kicks in about 10 decibels of extra noise whenever it switches on. Again, the plasma TV in the neighborhood, getting too near the Wi-Fi. It's well worth studying for psi and for health reasons.
So does your family complain when you turn off the air conditioner so you can communicate on your radio?
Actually, what they complain about is my radio comes over the telephone line.
Oh, so you're providing interference yourself. Okay. Right. All right.
Luckily only in the house, but of course it's a radio signal. So
Tamara says she thought that your use of COVID time was awesome, and she appreciates you sharing what you found. So that's good. Appreciate your participation. Thank you so much, Doug, for your presentation.